Well, so one of the things that I'm thinking based on it, this whole class is about tracking, and usually you're tracking things in multiple dimensions. The one-dimensional examples are, or if you're crazy like Sam, two-dimensional examples are okay if you want to compare it with the optimal tracker, but we're at a stage in the class where I think we should probably be working a lot more with the multidimensional problems and getting a handle on the impact of that. A lot of you, or at least some of you, had requested extensions. And what I'm inclined to do next week, instead of having the fifth and final homework assignment due then, pushing that out just 1 week and having more presentations from Reed and Nathan and probably Jeff next Wednesday for them to present on the same homework, since it's such a sort of important homework. So you guys get a heads up. Does that sound okay?
Yeah, that'd be great.
Okay, let's do that then, and we'll stay in this domain of working with these multidimensional problems for a while. I'm really eager to share with you about the Viterbi algorithm. It's a beautiful algorithm for doing tracking, and it'll be sort of the final variation before we move on to Kalman filter and some of the variations there. But I'll cover that on Monday, and today I'll just take you through one example of that I did on a multi-tracking problem. And like all of you, I wanted an extension, but I couldn't get one. So since as far along as I'd like, and I hope to expand this a little bit for Monday, and maybe to briefly go over some of the ideas and apply it to a real signal as well. What I have to share with you today is applying it to a synthetic signal. So one of the things that I've been interested in for a few years, and I've published on and even filed a patent that's about ready to be issued, is on using state-space methods for tracking cardiovascular signals. And in this context, you can imagine in intensive care units, in emergency rooms, even I was at a doctor's appointment yesterday, even I went in there and they stuck my finger in a little pulse oximeter. It was measuring my pulse rate and was acquiring what I'm calling a cardiovascular signal. These are signals that are measures of your cardiovascular system, whether they're invasive, non-invasive. An electrocardiogram, where we put the leads on your chest, you're measuring the electrical activity of the heart, blood pressure signals, optical signals like what I experienced yesterday. These are all cardiovascular signals, and they contain arguably a wealth of information that can help clinicians take better care of their patients. And they're already monitored today in commercial patient monitors, but the algorithms that are used to analyze them are heuristic. And by that, what I mean is some engineers sat down, analyzed the signal, and designed an algorithm using the filters and thresholds and detectors and tools that we're all accustomed to. And one of the things that I'm sort of proud of is part of my career arc as a contribution is showing that these cardiovascular signals can actually be tracked. A lot of the parameters that you're interested in can be tracked using state-space methods that we're talking about in this class. So it's really cool. And I'm going to give you an example, a simple example of a tracker that is applied with a particle filter for doing exactly this kind of tracking. But I want to give you some context on where this is used, also how it's used. So here's the model. The first thing here is we've got the angle, and not everyone, sort of sadly, not all engineers realize that the angle is related to the frequency by an integral, or in this case, in discrete time, it's equivalent to a sum. So the angle is equal to what it was at time n, plus the sampling period times 2 pi times the frequency. The frequency is in hertz. And so this is how the angle is calculated in units of radians. I want to keep in mind there's an inclination to think that the angle and the frequency, that this would be a constant plus some, I'm not going to get this right. People do this wrong often, but this is at least the right way to calculate what the angle is from the frequency. To use this, in this case, a sum. And notice there's no noise term added here. I am assuming that ignoring the fact that we're using a discrete time approximation, and we're assuming that the frequency is constant over the interval of each time sample, that otherwise there's no additional fluctuation in the angle. And so any fluctuation in the actual angle that we're tracking has got to come from the frequency itself. and the frequency itself does have a noise term that's added to it. Now there's some complications here, and these complications I think will be useful for some of your tracking applications. I have additional knowledge about what the frequency can be. We're talking about a heart rate. And the heart rate, I know, is not going to be less than half a hertz, less than 30 beats per minute, if you want to think in those units. And even if you're an athlete that's in incredible shape, it's very unlikely that your frequency, your heart rate is going to drop below 30. Athletes can have a very low heart rate, but not that low. Likewise, unless you are a newborn or a very young child, the maximum frequency of an adult heart rate is not going to be much above 2 hertz. 120 beats per minute is what that works out to be. If it is, then maybe you should go see your doctor. That's the expected normal physiologic range. And one of the things I've done here is clip what the frequency is going to be so that it's constrained to be within that range. And incorporating these limits in this way is something that all of you can do in a lot of your applications also, where you know that whatever it is that you're interested in tracking is constrained to being within some range. So,
talking about values at rest.
Pardon?
The values are at rest. The ones that
yeah, this is assuming at rest. It doesn't have to be. I mean, if you had a sports application, then you would probably want to use a different model. Okay. I'm mostly working with.
There for a second.
I'm mostly working with, if you're working out, if you're on the treadmill, then your heart rate is going to be higher. I'm mostly working with sick patients, and so people in a hospital are laying in a bed and they're not moving a lot. They may not even be conscious. Here I'm using a hard threshold. You don't have to use a hard threshold. You could use a soft threshold. And I am also doing something here that may be interesting. There's a mean frequency that I know that adults are going to have on average. Let's call it 60 beats per minute, for example. So 1 hertz. 60 beats per minute is the same as 1 hertz. And I know on average the frequency is going to be close to that. So far, what we've talked about for modeling are basically 2 processes. The things that we've been using the most frequently is x of... There's probably a way to adjust the default. X of n plus 1 is equal to what it was plus some noise. So this is what we're calling the random walk model. And this can wander off any place. It doesn't matter if the average is 1 or 5, if what you're trying to track. This can wander off and be whatever it wants to be. It's not biased on average towards any value. But we've also been using an autoregressive model sometimes, where you say x of n plus 1 is equal to some alpha times what it was, plus u of n. So this is the random walk model, and this is the autoregressive model. And the autoregressive model, if alpha is less than 1, which it almost always is, if alpha is less than 1, then the autoregressive model will bias your state estimates to 0. This is like taking white noise and applying it through a low-pass filter is one way of thinking about what this process model is. And on average, the output of this is going to be 0. It's not true. As soon as alpha hits 1, it's no longer biased towards 0. And how much it's biased towards 0 depends on how close alpha is to 1. The closer it gets to 1, the more variability that you have in your state and in your process dynamics. In this particular model, however, I've done something different because I wanted to bias it to something other than 1. I wanted to bias it, but not to 1. And so in this case, I've biased it towards a mean frequency, which I happen to know based on domain knowledge. This is part of the knowledge I'm bringing to the model design of what the frequency is. I know on average it's 1. And so I said the model of how it evolves is that the difference of the frequency from the mean frequency gets scaled by some factor, and then I add the mean back in, and then I add the noise. So this is like an autoregressive process, but it's biased to have a mean of whatever f bar is. This is something that may be useful for some of the things you're doing. Another thing that's in here that I want to make note of is that the, I wish it wouldn't rotate. It's going to drive some people crazy. Is that I'm using sort of a hard threshold here. If you were to draw what this function looks like, this min and max operation, it's a little bit like putting this through a function that looks something like this, where this is the max and this is the min down here. And when we start working with the nonlinear Kalman filters, this sort of edge can cause you troubles, because at that point a linear approximation is going to be very different if you're in the linear region versus if you're saturated. If you're saturated, it says it won't respond at all. With particle filters, this sort of thing causes far fewer problems. But with the Kalman filter variations, that becomes problematic. And then the other thing I've done is I've said I'm going to model this using basically a Fourier series representation of the signal. But unlike a Fourier series representation, I'm going to let the coefficients change over time. And I should have used, this should be denoted A sub k comma n as I had above. That's something I'll need to correct in these slides. Oops.
Theta and F are vectors? I mean, they're more than one component to them?
No. Theta is a scalar, and F is a scalar too. And the coefficients, you've got 2 coefficients for each harmonic, and you can have as many harmonics as you want, whatever is appropriate for your signal. You may recall there was a student in the NIR lab, I'm blanking on his name right now, but a student in the NIR lab who was also doing frequency tracking and took this class 2.5 years ago. And he was tracking frequencies of ships from the propeller as picked up by a hydrophone. George, thanks. And these same algorithms can be used for tracking those frequencies as well. Maybe relevant to what Pasang is doing as well. I don't know if she's trying to track frequencies and harmonics and Doppler shifts, but if she is, then using an algorithm like this for tracking signals that have harmonics and slowly varying frequencies works really well.
Yeah, she's defending next week.
Oh, so maybe it's a little bit late. Okay, well. Are there any questions on the model? These top 4 equations essentially comprise the process model, and this is the measurement model. No? You guys got it? Okay. Good. Just as we're getting to like the really cool part, but maybe just briefly, all the parameters we have to pick, the recording parameters. I chose a sample rate of 10 hertz, and I'm just going to do 500 samples. Because I'm thinking about cardiovascular, I chose the mean frequency to be 1 hertz and range from 0 to 2 hertz. I should have made that 0.5, but I didn't. I chose a frequency alpha of 0.98, just 2 harmonics, which is appropriate for things like blood pressure signals that tend to be very smooth and not have a lot of content much above the second harmonic. And then the noise parameters. I'll talk more about this to a real signal. I was a little bit inspired by Reid, so I usually am doing 100 particle runs, but I decided to push it up to 1,000. And I think actually this is right. I did set the resampling threshold at 25%. I'm just using the sort of vanilla version of the particle filter with resampling. Straightforward. There are some things that I haven't shared with you that I think will be helpful. So in this case, we've got a scalar measurement model, and we've got many parameters in the state space. We've got the angle, the frequency, and then 4 coefficients. We've got a total of 6. It's a 6-dimensional state vector that I'm doing with particle filters. And here you can see, so the red is the true measurement. It's got noise added to it, and so you wouldn't expect the tracked signal to be that different. I haven't talked about how to generate this from particle filters yet, and I will. Let me just say that when you're generating y hat, if you start generating an estimate of your measurements, what you shouldn't do is sort of the obvious thing. Y hat should not be set equal to f of whatever x hat is. Well, I guess actually I didn't do that right, because we usually call this h. Oh gosh. Let me go back. I didn't. So what you shouldn't do at time n is set this equal to your measurement model times x hat at time n. What you want to do instead is apply each of your particles and take a weighted average of the h. And I can talk more about that next time. I'll explain that. There's a number of places where that comes in. But in any case, show an estimate from the particle filter of what the measurement is. We haven't played much with that. Sam had asked the question of whether the number of effective particles is a good way of looking at whether you're tracking well or not. And the answer is no, probably not. But what is a good way of seeing whether you're tracking or not, if you've got the additive model that most of us are working with, is to look at what are called the innovations. I'll denote that as y tilde. And this is the difference between what your measurements were and what you estimated them to be using your particle filter. That difference, if you're tracking well, should be white noise. And so looking at that difference is a really good way of seeing how well your algorithm is tracking. If there's structure in this difference, if you take a spectrogram or you look at it in the time domain and you see things that are different than white noise, then that's an indication that there's room for improvement in your tracker. And I'll say more about that later as well. This shows how well it's able to estimate the frequency. You can see that initially it has no idea, it's jumping all over the place, and then suddenly it sort of locks on and stays locked on. That's very typical of trackers in general, not just particle filters, but all of the tracking algorithms, where initially they may not know, and then once they get a lock and they start tracking well, they stay locked, and they pretty much stay on it where it is. And you can see there are some places where it misses, but by and large it's tracking the frequency really well. This is a plot of the residual that I was talking about, and this isn't exactly white noise, but it's not too far either, and we'll look at it differently in a minute, but this shows the measurement residual. You can calculate this even if you aren't working with synthetic data. You always have your measurements, even if you don't have the true state. So this is something you can plot with real data. This isn't, and this is just showing the error in the estimated frequency.
So on top you have the innovation?
Yeah. It's mislabeled, I'm sorry.
You may want to,
yeah, I need to fix the label, thanks for that.
I was thinking of myself, going back to that slide. 5 days from now, I wondered.
Yeah, I'm glad we got that on the recording as well. So you've all seen this before. This just shows the resampling and the weights, and this shows the number of effective samples. You can kind of see this threshold was about 250, and it does exactly what you would expect and what we've seen it do many times before. This shows a spectrogram of the original signal, and I've plotted on top of it what the true frequency was and what the estimated frequency was from the particle filter. And so in this case, you look at it and you're like, oh, it's doing really well, it's nailing it. And we can also see the second harmonic and nothing above it. All this other stuff, there's not a harmonic up here, this is just noise. And you can see that the second harmonic is somewhat faint, it's weaker than the fundamental frequency. So, and then this is something that you can generate. This shows the spectrogram of the residuals. And if you look at this, and it looks like white noise, which this mostly does, then you have confidence that you're tracking about as well as you're going to be able to. So this is really good. I was very happy.
That only applies to the additive noise case?
Yeah, I'd have to think about the nonlinear case. Additive noise is so common that it's what is at the forefront of my mind. It's probably different when you have non-additive noise. Yeah, if you had multiplicative noise or some nonlinear function of the noise, then it'll be different. Down here at the bottom, this is the angle, and the angle increases more or less linearly with time, as you would expect. It's an integral of the frequency, and I didn't wrap it as I could have. I just let it increase rather than showing it go up and then cutting it off when it's 360 and knocking it back down to 0. And you can see initially there were a lot of particles that were sort of not at the right angle, and then suddenly it sort of figured it out and then stayed right where it should be all the way through, and that was great.
Stayed some offset and then gone up with that same.
Yeah, that's a really good point, Sam, and it didn't in this particular run. It's a little bit like yours. When I did this with 100 particles, I did see that, and when I increased it to 1,000, it didn't, and so I thought, great, I'm not going to have to talk about it today. But you're right, it can lock in where there's an offset. It's possible, and it just didn't in this particular run.
I mean,
but that is a good point.
Right.
Yeah. Well, and there's more to it also that I won't get into. Maybe I will if we have time on Monday. And then maybe the last thing I'll show you is this, which shows the trajectory of the estimated frequency. These are all the individual particle trajectories, and you can see them sort of blow up and then condense whenever there's a resampling event. And I did post this code, so if for those of you that are working from my code, you might use this code when you're working with a multidimensional case. It should be pretty easy to adapt, and it already will cycle through and now handle the multidimensional case, where it'll cycle through and generate a separate plot for each one of those. So that should be really nice. And this shows, again, what the real frequency is, where it is, and the estimated confidence intervals. I did display on the slide what percentage of the time this was within the 95% confidence interval, and it was less than 95%, but this is only 500 samples, and these are not statistically independent of one another. If it's out of the confidence interval here, then it probably will be in the next sample as well. So there's a wide confidence interval on this confidence interval, if you will. And if I ran this out 5,000 samples instead of 500, then I expect that would be pretty close to what the true is. So, and I did it for the coefficients also, and there's a longer story behind these, but maybe I'll talk more about that on Monday. We're already a little bit over time now. But that gives you another example. I think we saw some really nice examples today of multi-dimensional problems, especially the salmon tracking, which is very common where you're tracking something physical, and in this case, trying to track a heart rate, which we know changes, but changes slowly over time. Those are, that's the kind of thing you should have in mind as you're thinking about different applications for the algorithms that we're talking about in this class. So I see the other classes waiting for us. We'll stop there, and I'll see you guys on Monday. And I'll update the homework assignment. So Jimmy, don't download it today.